if you do a standard thing that meteorologists do is you look at 30-year time series as to establish climatology, and then you can test statistical significance of changes against the natural variability of climate. And so here's for the double CO2 case, basically the temperature change is statistically significant everywhere. For just this 1.8% reduction in solar intensity, there's still some residual statistically significant climate change over 12% of the Earth's area at the 5% level. So you'd expect 5% of the Earth to be statistically significant just by chance. Now, this is an untuned system. If you go back to this other slide, you can see there's still a little bit of warming at the poles, and you can imagine a system that would put in more aerosols around the poles. And so, if the most crude thing does this good a job, you would think, well, something a little more sophisticated would do a better job. And then if we look at precipitation, the statistically significant precipitation, that that basically what you get in a global warming situation is more net evaporation around the equator, and then more water vapor transport to the high latitudes and more precipitation at high latitudes is a common feature of climate model simulations. And basically what we found with the geoengineering is that in this sort of idealized geoengineering, that precipitation changes are only statistically significant over 4% of the Earth's area. You'd expect it to be over 5% just by chance. So basically it's saying it's doing, within the detectability of this test, a perfect job. Now this is a point-wise statistical significance. It turns out there actually is less precipitation in this case overall, but that would be statistically significant if you average over, say, all the land area of the Earth. But there's enough climate variability at any given point that it's not statistically significant at any given location. And so it seems to do a pretty good job both at reversing changes in temperature and the hydrological cycle. And this is pretty, with a very crude approach. It's basically just blocking sunlight top of atmosphere. So, the first objection, we published these kind of results, and people said, oh, but won't this hurt the biosphere because you're reducing sunlight and plants need sunlight for photosynthesis? And, the one observation, first of all, is that after Mount Pinatubo, by looking at carbon isotopes, you can tell whether carbon is going into the ocean or the land surface, and also by looking at oxygen-nitrogen ratios. And basically the rate of CO2 decreased after Mount Pinatubo, and after some investigation it was concluded that forests actually grew better even though there was a couple of % reduction in sunlight. And that's because while there was maybe something like a 2% reduction in overall sunlight, there was something like, I forget the exact numbers, but maybe something upwards of up to 20% of the sunlight was converted into diffuse radiation. The diffuse radiation is able to penetrate deeper into forest canopies, and it looks like that photosynthesis in forests actually went up even though overall sunlight was reduced because the lower leaves were better lit and able to grow more vigorously. And so at least the observations after Mount Pinatubo is the biosphere grew more vigorously. In our simulations also the biosphere grew more vigorously in a geoengineered world, in the sense that the plants are constantly trying to get enough CO2 for photosynthesis, and they're controlling their stomatal aperture, so basically pores on their leaves, in order to get that CO2 in. When they open up their pores or the stomates to get the CO2 in, they lose water. And so by having more CO2 in the atmosphere, the plants can keep their stomates closed, and so they lose less water, and so they use water more efficiently, and this leads to eventually the biosphere supporting more productivity. And at least in our simulations, this effect The effect of sunlight on photosynthesis is basically linear, so that it's sort of a 2% reduction in sunlight is more or less a 2% reduction in photosynthesis. And so in this simulation, at least, the CO2 water use efficiency effect was much stronger than the reduction in photosynthesis due to the reduced sunlight, and the result was that the biosphere, at least in the simulation, was much more vigorous. Now, you know what that means for the real world. Now, I have to say that some of my colleagues have gone around touting these kind of results as saying, oh, this is encouraging, and it says that you know, somehow the world, a geoengineered world, will be better than even the natural world. And I think this is a misguided view, because especially for natural ecosystems, you know, that even something that makes a natural ecosystem grow more vigorously is a perturbation to that natural ecosystem. It's not necessarily good for the ecosystem. You know, we see putting more coastal eutrophication, putting more fertilizers in coastal waters is not good for coastal ecosystems. It's disruptive, and in the same way, this could be disruptive to ecosystems. So, you know, one of the questions is, if we were confronted by a climate emergency, and I'll leave it up to you to define what that might be, you know, how long would it take for a geoengineering scheme? I didn't make the whole sentence there. How long would it take for a geoengineering scheme to become effective? And we did some simulations last year, published in the Proceedings of the National Academy of Sciences, where we basically turned on geoengineering schemes. So we had this background red curve, which was a global warming simulation, one of the IPCC scenarios, and then, you know, at different years, kind of turning on geoengineering to try to reverse this. And as you can see, that, you know, the temperature effects are seen, you know, in the subsequent year, or almost immediately. And the same is true of Mount Pinatubo. The next year was cooler, and that it continues cooling very dramatically for a decade or two, and then you have slower cooling after that. And so, you know, and in contrast, if you would say, well, what is the time scale for response to a reduction in CO2 emission? That you know, that even if we eliminated emissions entirely tomorrow, that that would be enough to stabilize temperatures but not reduce temperatures, and that the full climate effect of a CO2 emission, or most of the climate effect of a CO2 emission, is not felt for several decades. And so, as I said, even if we went to zero emissions tomorrow, that would be just enough to stabilize temperature and not even reduce temperature. And so if we were confronted with some kind of catastrophic situation, that really emissions reduction is not even an option for reducing temperatures in the short term, but these geoengineering schemes are. This is sort of the flip side of that, is that if you had a geoengineering scheme and you were keeping your Earth cool, and then the system should fail at some point, you'd get the opposite thing, that you'd get a huge amount of warming right away. And so, you know, and this could fail either for technical reasons or political reasons, or there could be a war or something. And so if you were masking huge amounts of warming by doing these geoengineering options and they failed, you could get rates of warming that were, say, 20 times faster than what otherwise would have occurred. The other point here on this figure is that we really don't know how much the Earth will warm due to a doubling of CO2. That there's an uncertainty in climate sensitivity. And if you continue geoengineering the planet, you might never actually find out what climate sensitivity is. And so the dashed lines are a case where the Earth is very sensitive to increasing CO2 content. The solid lines are where it's less sensitive. And so in the geoengineered case, you're both on those purple lines at the bottom, basically, you know, you're down here and you're masking climate change. And if you stop the system, if climate sensitivity was high, you'd sort of rebound up towards that dashed line. If it's lower, you'd rebound towards that line. And so anyway, geoengineering might prevent us from learning how much climate change we're masking.